Hey guys, welcome back. Last day of new stuff, but before we get to it, time for some funnies. So this happened last year during an intruder drill. We had to block out the window and put up a bunch of paper. And while I was putting up the paper, I thought, wow, if this was a real intruder, we should send him a message. What a great idea. Because the whole point is we're trying to pretend like nobody's there, right? So we wrote the intruder a message, and we told him, I'll let you read it yourself. I didn't write the message. One of my students did, but I suppose I helped him tape it up, so it was kind of funny. Anyway, good times. It's good to have funnies. All right, so let's do our last stuff, which is side-splitting theorem, triangle angle bisectors, and the transversals theorem, which is the same thing as side-splitting, by the way. All right, so side-splitting theorem, which is really angle-angle similarity, says that if we have a triangle where we have two sides that are parallel, the other parallel side is going to split that triangle with proportional sides of the other one. So, and the reason for this is because this parallel line here is going to have the same corresponding angle that we see on the other parallel line, which means that, and also this angle is going to be the same for the two triangles here. And so what's going to end up happening is that if these two angles are the same, then all the sides are going to be proportional. At least the extensions are going to be the same proportion of the other side. So these two sides here got split proportionally. Now the third side is going to be proportional to the sum of the first two to the first one. So there's a distinction there, and we do need to make sure that we see that. But the two sides here will be split proportionally. And no matter where this point goes, so even if it was smaller or even further out, it's still going to, the extension is going to be proportional to the original part. So the original small triangle and the extension is going to be split proportionally, which is kind of cool. So what we can end up saying is that AB, so AB here, goes to BC, which is the extension for BC, just as AD goes to its extension, which is DE. So basically that's it. And the side-splitting theorem requires that the two lines be parallel, and if the lines are parallel, then they're going to split. These two will be corresponding angles, so they're going to be congruent to each other, and that means the triangles are similar by angle-angle similarity. All right, so an example of side-splitting theorem, lots of different ways we can set it up. Again, these lines are parallel, so we've got corresponding angles on the bottom. That angle is the same. These are also corresponding angles up here, by the way. So we can say that 2.5 goes to x just as 3 goes to 6. We could also set it up where 2.5 goes to x just as 3 goes to 6, just setting it up horizontally or vertically, either way. And then x goes to 6 just as the extension 2.5 goes to the extension of 3. If we wanted to solve for this, we could actually pretty easily do scale factor, right? If you notice, we're multiplying everything times 2 from the extension back to the original. So if we go from the extension back to the original, times 2 is going to give us 5, right? So this x is going to be equal to 5, sure. And you get the same thing if you cross multiply any of the proportions. But often it's easier to just do scale factor instead of actually setting up proportions, if you can see it. All right, the only pretty much other thing we have is a triangle angle bisector theorem. So if we have a triangle, which is our big triangle here, and one of the angles is bisected, meaning it's cut in half by this segment, then the segment is going to cut the opposite side in proportions to the other two sides of the triangle. So let me say that again. If we have a triangle angle bisector, so this segment is going to bisect this angle, it cuts it in half, then it's going to cut the opposite side in proportions to the other two sides of the triangle, which is pretty interesting. So if we set up a proportion for it, we would say that AB goes to BC just as AD goes to CD, and that would be our proportion. So this cuts the opposite side here proportional to the other two sides. So if those sides are proportional and these angles are congruent because they were cut in half, the next question I would have is, are these two triangles going to be similar to each other? Well, if you just look at them, they're not the same shape, right? One of them is an obtuse triangle with this obtuse angle. The other is acute. So they can't be similar, but two of their sides are proportional and one of their angles are congruent. So what's actually happening here is we have angle, money sign, money sign. Remember that? Donkey postulate's going on, right? So can we use the donkey postulate for congruency? No, unless we have a right angle, and then it's called the hypotenuse leg theorem. Well, the same exact thing's happening here with similarity, and it's kind of cool because it's the triangle angle bisector theorem, so it does apply with similarity as well. We cannot use angle, money sign to prove similarity unless we have a right angle. So what's ended up happening here is these two angles, which one is acute, one's obtuse, if those were congruent, meaning this was cutting it in half, the only way that would happen is if this was an isosceles trapezoid, or sorry, an isosceles triangle, by the way, which would mean that this diagonal would cut it at half where it's perpendicular here. So that's the only way, which is if the other two sides are congruent, then it would cut the other third side in half as well. And you can kind of imagine what that looks like, or maybe, hopefully you can. So the whole point of geometry is hopefully you're able to like visualize what's going on and differences. So I'll try to bring most of the visuals to you, but some of this you gotta do on your own, I suppose. So yeah, donkey postulate, does it work? No, unless we have a right angle, and unless these two here are right angles, and they're not, because these two sides are not proportional, or they're not congruent, but they are proportional. Okay, so triangle angle bisector, if we have a segment that cuts an angle in half, it's going to cut the opposite side in proportions to the other two sides. The other thing you might notice, let me clear all this stuff, is that this side here is congruent, right? So two sides were proportional, okay, but the third side is congruent. So it's not growing at any rate. The other two are growing or shrinking, but this one is not growing at all. So it can't be truly, it can't be, I'm trying to think what I'm trying, it can't be similar unless all these sides are going to be congruent. So that's really the only way this would work, which would be kind of like the hypotenuse leg theorem. So this side's the same, those two sides are the same, those two sides are the same as well. That's the only way this would work. Okay, let me, sorry, I just have to do it. But let me go ahead and draw an isosceles trapezoid here, or isosceles triangle, and you can see what I'm talking about. So this angle cutting down the middle is going to bisect the top angle right up here. And because the opposite sides here are the same, that means this is going to be a right angle and it's going to cut these. And so the only reason that these are going to be similar, and we could do angle, side, side, the only reason that they're going to be similar is because we know it's like the hypotenuse leg theorem. We can't do a money sign, but we can do it if the sides are the same. Then it's the hypotenuse leg theorem. So anyway, cool stuff. Hopefully you caught all that. Probably not the best explanation, but you know, doing what I can. All right, triangle angle bisectors. So let's see this in play here. So this I constructed so that this angle would be an angle bisector. So it's always going to adjust and cut the angle in half. And then the other, the side that it cuts here is not going to be cut in half, but it will be cut in proportions of the other two sides. So if you set a proportion, this goes to this, just as this goes to this. And regardless of what I do, it's always going to be true. Whoa, kind of fun. Super fun. Whoa. Kind of cool. Okay. Mesmerizing. So an example of triangle angle bisector, we have 4 goes to 2x, just as x goes to 9. Lots of ways you can set it up. So 4 goes to, okay, so I'm doing 4 goes to x, just as 2x goes to 9. And on this one, we could reduce it if we wanted to, because 4 divided by 2 is just going to be 2. But I'm going to leave it unreduced just for here. So 2x times x, ooh, x times x is x squared, so it's 2x squared is equal to 4 times 9, which is going to be 36. Oh my gosh, what do we do with an exponent? I know I did this on purpose, so you'll be all right. And the next unit, we are going to be dealing with a lot of exponents with radicals and squares, so make sure we know how to do it. All right, so next thing we want to do is divide this 2 from both sides. So divide by 2 gives us x squared, not what I was trying to do. Anyway, x squared is equal to 18. And then how do we undo a square? Well, spoilers, we take the square root, which is a 1/2 power, because a half power of 2 is going to take it back to 1, which is our exponential identity. Remember that whole thing? All right, so the square root of 18 is going to be our answer. So x is going to be the square root of 18, but we can actually reduce that. So we're going to do kind of like this factor tree, and we're going to break it down into a unique product of primes. So that's going to be 2 times 9. 9 can be broken down again as 3 times 3. Now, if we have 2 3's, we can actually take it out of the radical, which will leave us with x is equal to 3 radical, and then the only thing left in it was 2. Now, if all that sounded like nonsense, you have no idea how to simplify radicals, that's okay, because that's the next thing we're going to be doing next Thursday and Friday when we start off on our next unit with right triangles. So we will go over that stuff again with the shoe store example and everything, and you'll be fine. All right, so example number 2, same thing. So 8 is going to go to, I don't know, x. So 8 goes to x, just as 10 goes to 5. Now on this one, we could cross multiply and we get 10x is equal to 40, so x is equal to 4. That was easy. Or you could notice your scale factor. So if I look here, if I'm going from 10, or let me actually change that direction. If I'm going from 5 to 10, no, I need to do it the other way because that matches what's going up on top. So if I go from 10 to 5, I'm dividing it by 2. So if I go from 8 down here, I'm also going to be dividing by 2, which is going to give me x is equal to 4. All right, wonderful. Or you can just set up and solve the proportion. All right, next one we have is transversals. So if we have a set of parallel lines and two transversals that are cutting those parallel lines, it's going to make a bunch of corresponding angles, and basically the sides that it's going to make between them are going to be proportional. So AC goes to BD, just as CE goes to DF in this case. So just as you would think, and then you can cross multiply and solve. Now the reason this is happening is because these corresponding angles are going to be the same, top right, and the corresponding angles on the other transversal, top left, are the same as well. And I don't know if you see them, but there's a big triangle here and then an even bigger triangle on the bottom. And what do we know about those two triangles? Well, that's actually the side splitting theorem, right? So if we have parallel lines that are cutting this triangle, this angle up top is going to be the exact same angle, right? So that angle is the same, that angle is the same, and that angle is the same, and that is the same. So those triangles are going to be similar by the angle triangle similarity postulate, and so that means that their extensions here, AC going to CE, is going to be the same proportion as BE or BD going to DF, that one as well. So this really, the transversals is really the same thing as the side splitting theorem, which is kind of cool. So let's do an example. So 12 is going to go to 2x plus 4, just as x goes to 2x. And on this one, if I wanted to solve, the first thing I'd probably do is reduce that, which is just going to be 2 over 1, and then I can cross multiply. Actually here, you notice these all have a 2 in the terms as well, so we could take a 2 out of these as well. So that's going to leave me with, on the top, x plus 2, and on the bottom, just a regular x. So now when I cross multiply, I get 2x is equal to x plus 2. So therefore, if we subtract x from both sides, minus x, we get x is equal to 2. Oh, okay, nice. So if I plug it in, that would mean this is 4, and this is going to be 4 plus 4, which is equal to 8. And does that make sense? Yes, because our scale factor here is we're multiplying it times 2, right? So times 2, and then 4 times 2 is also 8. Yeah, so we know we did it right. Okay, groovy. So let's look at the transversals here with GeoGebra real quick. So on this one, these lines are all parallel. We have our transversals. So this extension goes to this extension, just as that one goes to that one. Or you can go across as well. That one goes to that one, just as that one goes to that one. And the reason this works is, again, because if I go all the way up here, they intersect at a triangle. This angle is the same for both triangles, and we just have really 3 triangles: the small one, the medium one, and the large one. Yeah, and so their extensions are going to be by the side splitting theorem, because all these are congruent or similar triangles by angle similarity theorem. Then their extensions are going to be proportional, because all the sides are proportional. Okay, so let's go ahead and start the assignment. So just 13 minutes, not that bad, honestly. I'm going to do quite a bit of the assignment with you too. So we want to, using the transversals here, which are all similar triangles, essentially, their extensions are all going to be proportional. We want to finish setting up the proportion. For some reason, looks like I deleted that. I'm going to fix it real quick because it matters. Okay, so A goes to C just as what goes to F. Okay, so A goes to C just as blank goes to F. Well, certainly it's going to be D, right? All right, A goes to B just as blank goes to E. So A goes to B just as D goes to E. Okay, so that one's D as well. Just follow the pattern. A plus B, so these two together, goes to C just as these two together, D plus E, goes to F. All right, number 9. So side splitting theorem, again, we know these are corresponding angles are going to be congruent, and this angle is the same as well, and then these angles over here are going to be congruent as well. So these are similar triangles, meaning the extension is proportional to the other sides. So lots of ways we can set it up. I'm going to say 18 goes to 6, just as x plus 3 goes to 4. Now before I multiply, you can actually reduce this, which is going to be 2... Or sorry, let me try that again. I'm getting ahead of myself. So this is going to be 3 over 2. And then you can reduce the 18 and the 3, because remember, if we can set it up vertically or horizontally, we can reduce vertically or horizontally. So 3 goes into 18, 6 times? And that's going to be left with just 1 up here. All right, then when I cross multiply, I'm going to have 1 times x plus 3, so just x plus 3, is equal to 6 times 2, which is going to be 12. And then all I do is subtract 3 from both sides, leave me with x is equal to 9. Now, if you didn't reduce first, you'd have to do some distribution, and it's going to be a little longer, but it'll work either way you want to do it. But anytime we can reduce vertically or horizontally before we cross multiply, it's going to make your numbers a lot easier to work with, more manageable. Number 12, the angle is being cut by this angle bisector, meaning it cuts the opposite side in proportions of the other two sides. So in other words, 4 goes to x, or you can say 4 goes to 20, just as x goes to 16. So lots of different ways you can set it up. I can reduce, right? So let's do that. On this one, we can factor out 4. So we got 4 on the bottom, 5 up here. And then 4 and 5, 4/5 can't be reduced, so we're done. So when I cross multiply, I get 5 times x, or 5x, is equal to 4 times 4, which is going to be 16. Divide by 5. Got to do it to one side, I do it to the other side. For some reason, again, these don't like to. Animations have been really messing up. How about now? Okay. So anyway, that's going to leave me with a decimal when I put it in the calculator, which is 3.2, I believe. All right, number 13. Now, what you need to notice is on this brace here, that's going to be the length of the whole thing. So it's this side plus this side. So don't let that trip you up. It's not just this side, it's the whole thing. So again, they're parallel, so transversals. If I extend these out, they're going to be similar triangles because the angles are the same. So 35, the whole thing goes to, the whole thing over here, which is 20 plus 8, which is 28. So the whole thing, 35, goes to the whole thing, the sum of these two, 28, just as the small part x goes to this small extension of 8. Now, I want to reduce, or you don't have to reduce. Yeah, let's reduce. All right, so on this one, it looks like 7 can go in both of those, so that's going to be 5, and this one is 4. And then you reduce 4/8, which is going to be 1/2. Okay, now that I've reduced, I can multiply 1 times x, which is just x, is equal to 5 times 2, which is 10. Okay, so this one here has to be equal to 10. And yeah, looks right. I don't think there's an easy scale factor. It's times 3.5, right? So 10 times 3.5. 3.5, and so 8 times 3.5 should also give us 20, and it will because they're proportional. But that's one you probably won't be able to see the proportion. You just need to do set up a proportion instead of doing scale factor. All right, number 16. So on this one, again, we have a triangle angle bisector. It's cutting this angle in half, meaning it cuts the opposite side, which is a full length of 18, by the way, into proportions, where one of the sides is x here. So what we first need to find is, we know that we need to find the length of the red side. So to do that, if the whole thing is 18 and this part is x, how do we write as an expression the length of the red side? So the whole thing is 18, this part is x. So this is going to be 18 minus x. So we have basically 10, and we can set up our proportion now. 10 goes to 15. I should have changed the colors, but you get the idea. So 10 goes to 15, just as x goes to 18 minus x. Now, before I cross multiply, I am going to reduce and take 5 out of both of these. So that's going to be 2 and 3. And there's not a 3 in both of these terms, so I can't reduce, and that's not going to help me either. So I'm going to do 3 times x. So 3x is equal to 2 times that. Now, when I multiply the 2 times that, it is going to be in parentheses, not just 2 by the 18. But you're going to need to distribute the 2 through to both of these terms. So we end up with 3x is equal to 36 minus 2x. Okay. Now we can add 2x to both sides because I want to undo subtraction. So I'm adding to both sides. So I have 5x is equal to 36. Then I divide by 5. Once again, this is... and there's your answer. Anyway, for some reason it's not showing up, but we want to divide by 5 again, and then that'll leave us with 7.2. If you put it in the calculator, give you a decimal. All right, number 21, again, triangle angle bisector, cuts the opposite side in proportions of the other two sides. So 2 goes to x plus 4, just as 3 goes to 2x plus 2. Now on this one, you can't reduce because there's not a 2 or 3 in both of those, and these don't have those, so you just have to cross multiply. So I'm going to get 2 times 2x plus 2 is equal to 3 times x plus 4, and I'm going to have to distribute on both of these. So when I do that, I get 4x plus 4 is equal to 3x plus 12. Okay. Then subtract 3x from both sides, leaving us with x plus 4 is equal to 12. Then subtract 4 from both sides, so x is equal to 8. Not that big of a deal. And in case you're curious, if we plug that in, that would give us 12 over here, and then 16 plus 2, which is going to be 18. So 2/3 and 12 and 18 reduces, taking out a factor of 6 to be 2/3 as well. So yes, that's true. 26. Business district of a town is shown on the map below. Maple, oak, and elm are parallel. So elm, oak, and maple are all parallel. First and second street are your transversals. Find the value of x, which is the length of first street between oak and elm. So it's, if these are transversals and these are all parallel, they're all extensions of some similar triangles because the corresponding angles are the same. So I can set up a proportion. They're going to cut each other proportionally. So x, or 350, goes to 300, just as x goes to 1650. Now on this one, you're going to end up just putting in the calculator 350 times 1650 divided by 300. But we could also reduce this if we see there's zeros. You could also reduce it, take 10 out of those two, and do whatever you want. Okay, so I'm just going to reduce those two because it's easy. So I end up with 30 times x, or in other words, 30x is equal to 350 times 165. Okay, so next step would be to divide by 30. So this is basically what you're going to put in the calculator. And if I didn't reduce the zeros, you just have an additional 0 here. It's not that big of a deal. So we didn't divide it by 300, and we'd be multiplying by 1650. All right, so anyway, when you put that in the calculator, you'll get 1925. So the length of First Street here is 1925. And then if we want to know how long is First Street between Elm and Maple, that's the whole thing. So we got to add the 350 to it, which will leave us with 2,275. All right, the last example I'm going to do with you is number 28. So on this one, we do have all three sides. So we could prove similarity with side, side, side. But if we have vertical angles in the middle, we really just need to show that the two sides that are including that angle are proportional. Then we're using side angle side. Well, we'll check. Okay, so on this one, we have the smaller one of 5 is going to go with the smaller one of these two of 10. So that is kind of tricky because it's really twisted. So you have to be careful. The biggest one of 6 is going to go with the biggest one of 12. And I'm just going to tell you right now, this type of problem is probably one of the most missed problems from the test. So probably a good idea to make sure you remember that. So the smallest side of 4 clearly goes with the smallest side of 8 over here. The medium side of 5 goes with the medium side of 10. And the biggest or longest side of 6 goes with the longest side of 12. Really, you just have to look at the ones in the middle. So is this true? Well, if we reduce the fractions here, sure enough, that's going to be 5, 6 is equal to 5, 6. So when cross multiply, it's all Gucci. The other way, if you just wanted to cross multiply without reducing, we would get 60 is equal to 60. So sure enough, they are indeed going to be proportional sides. And so the two triangles are going to be similar by side included angle side. The same proportional side here, included angle proportional side. So yes, by side angle side. Now we could also set up another one on the other side where we could say that, I'd have to change the way that I set up my extended proportions if I do all three. But you can also look and see there's a scale factor. So if I'm going from 5 to 10, I'm multiplying it by 2. 6 times 2 is 12, and 4 times 2 is 8. So they all have the same common scale factor of times 2, or the same common ratio of 1 to 2. So sure enough, you could do this by side, 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 or side angle side. I'm not sure what the answer bank says, but if there's one of them that's 2, it's going to be number 28. All right, so that's it. 25 minutes, not too bad. I'll see you guys later. We're just going to do a review and then a practice test for the rest of the week. Then when we come back in person, our first day back, we'll be taking the test. If you're a distance learning student, you probably noticed this. I'll post a test for you after my B students have taken it. So that'll be next Thursday, probably around 3:10 again, just like I did last week. And then after we take the test, the next day we'll do our golf game, which is going to be a lot of fun. So we'll be able to play against a partner. So looking forward to that. And then we'll do the same thing. We'll do remediation. We'll talk about what you guys are missing. And then the next week after that, we'll do our retakes. So we did retakes at the beginning of this week. And of course, everyone's grades can only go up from doing the retakes. And so the ones that finished their homework and figured out what they did wrong on the test, grades went up. So that's wonderful. Some of you guys are still struggling with that. And so your grades are still not doing too well. So really got to do your homework, and then we can do retakes later once you get your homework done. So see you guys later, and have